Good evening everyone, good evening. Welcome you all again to NEET Elite. Hoping that you guys are doing great, having a good time. Well people, just let me know in the chats if I'm audible and visible to everyone. Hello Vivek, hi Simran, hi Ishpreet, hello Zahran. Hello Dinesh, hello Chitra, hello Maria. Hello Sweetie Tiwari. Welcome back, hello Fazan, hi Shreya. Hello Ashika. Hello Suzina, hello Sharanya, hello Sundar. Welcome back everyone, welcome back. Just give me some green signal from the chats so that I'll get to know that I'm audible and visible to you. Yes? Let me know first of all in the chats if I'm audible and visible to you guys. Give me some green signal from the chats, yeah? Perfecto. So people, as you all must be knowing, tonight we are going to start the chemical bonding actually, right? So what all things we are going to cover in the tonight's session? We'll be starting with exact basics. We'll be starting with something called as chemical bond. We'll see exactly its types, ionic bond. Then we'll later on move into the covalent bond, right? And in the covalent bond, we'll be discussing about the Lewis structures and the formal charge as well, right? Well, these are the topics which I'm going to cover in the tonight's discussion over here on this NEET Elite channel, yeah? Well, the ones who are new to the channel, let me introduce myself. Well, people, my name is Wassim Sir and I'm your chemistry master teacher right here on this NEET Elite channel, right? And the ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this NEET Elite channel, yeah? So do like the video, share the video with your friends, and do subscribe to the channel as well. Welcome back everyone, welcome back. Okay, yes Vivek, exactly. Well, tonight on Vedantu J English channel, I'm going to start chemical equilibrium also at 10:30 tonight sharp, right? Well, after this session, you can join me on Vedantu J English channel in which I'll be starting a new chapter, that is chemical equilibrium, right? So that 2 chapters will go parallelly for you all, yeah? So people, before starting the session, you guys can let me know in the chats if you guys are super duper excited about the tonight's session as well, right? Well, these are the things which we are going to cover in the tonight's session. We'll start with chemical bond, then we'll be moving into the ionic bond, lattice energy, hydration energy, covalent bonds, Lewis structures, and formal charge, right? Just let me know in the chats if you guys are super duper excited about it, yeah? That's wonderful. That's wonderful, guys. Perfect. Perfect. So without wasting a lot of your time, let's get going. Let's get started with something called as chemical bond. The point is, how do we define the term chemical bond, right? What is chemical bond all about? Any force of attraction which holds the atoms together in a molecule, right? In general, I'm talking, right? Any force of attraction that holds the atoms together in a molecule is something which we call as chemical bond, right? Whatever force it is, any force which holds the atoms together in a molecule is something which I'll be calling as chemical bond, right? Well, people, this is something which every one of you must be knowing, yeah? The point is, how many different types of chemical bonds do we have, right? Let's get going, let's get started with the first type of chemical bond, which is what we call either as ionic bond or the electrovalent bond, right? Let me first of all make you understand what this ionic bond is all about. Understand properly what I'm going to say, yeah? Or let's read the definition of this ionic bond first, then I'll make you understand, right? This is the definition which is mentioned on the screen. Well, people, the chemical bond which is formed between 2 atoms due to complete transfer of electrons. Is either called as ionic bond or you call it as the electrovalent bond as well. Now the point is, what is meant by that? What all things do we have to understand from this definition? See, for example, if you take the compound NaCl, right? Let's say I'm taking the compound NaCl, right? See, NaCl is an ionic compound. Why it's an ionic compound? See, why it is an ionic compound? Let's have a look on that. See guys, first of all, in case of NaCl, you have got 2 elements. One is sodium, one is chlorine, right? As you all must be knowing, sodium, it is the example of the typical metal, right? And chlorine is the example of the typical non-metal. yeah? And metals have got strong electropositive character. Metals have got high tendency to lose the electrons, right? This Na positive, it is electropositive in nature. It has got strong tendency to lose electrons because it's a typical metal, right? It's a property of the metals to lose the electrons. Yes. Similarly, this chlorine is a non-metal, right? So it is basically electronegative in nature, as you all must be familiar with the fact, right? See, first of all, this NaCl, this sodium chloride, it's made up of two elements. One is sodium, one is chlorine. Sodium being the metal, which is highly electropositive in nature, right? Chlorine being the non-metal, highly electronegative in nature. If sodium is the metal, if sodium is electropositive in nature, if I ask you how many electrons are there in the outermost shell of sodium, you'll say 1 electron, right? Because sodium, it belongs to group first elements, right? It belongs to alkali metals. Alkali metals have got 1 electron in the outermost shell. So what this sodium is going to do, this sodium is going to lose that 1 outermost electron from it and gets converted into the cation like this. This is the cation to which the sodium got converted, right? Now this 1 electron, which is actually given by sodium, sodium has lost this 1 electron completely, right? So this 1 electron, which is lost by sodium, this 1 electron will be gained by chlorine, right? And chlorine will be getting converted into the N ion, which is Cl negative, right? So basically metal lost the electron, got converted into the cation, yes, and non-metal, it gained the electron, got converted into the N ion. So people, over here I got two charged species, one carrying the positive charge, one carrying the negative charge, right? So over here I got two charged species, one carrying the positive charge, another one carrying the negative charge, right? Well, if I got two species, one carrying positive, one carrying negative charge, can I say there will be electrostatic force of attraction between these two charged particles? And this electrostatic force of attraction between these two charged particles, this is something which you either call as ionic bond or you call it as the electrovalent bond. You call it as the electrovalent bond as well. Yes, this electrostatic force of attraction between the cation and the anion is something which I'll be calling as ionic bond, or you call this as the electrovalent bond as well. Why you call it as electrovalent bond? Because it involves, this bond formation involves complete transfer of electrons. I can clearly say one of the electron has been lost by this sodium and that electron is gained by this chlorine. So complete transfer of electron is taking place. Sodium is losing its electron and chlorine is gaining that electron completely. So complete transfer of electrons is taking place. And whenever in any kind of bond formation, complete transfer of electrons takes place, which leads to the formation of cation and the anion, then there will be electrostatic forces between them, right? And that electrostatic force of attraction is something which I'll be calling as ionic bond or electrovalent bond. And any compound in which ionic bond will be present, we call that compound simply as the ionic compound. Yes, I'm sure it's clear to everyone. You can let me know in the chats if it is clear to everyone so that I can move on, right? Let me know fast in the chats, people. I'm looking at your chats only. Yes, perfect. Yes, Richard, you can watch it. Wonderful. So what are the conditions for this ionic bond to get formed? Let's talk about the conditions for the ionic bond formation. What are the conditions which must be satisfied for the formation of the ionic bond, right? Well, people, few minutes back only you saw ionic compound contains two elements, right? One is metal, one is non-metal. Metal, highly electropositive. Metal should be electropositive, non-metal should be electronegative, right? Then only your metal can lose electron, get converted to the cation, and that electron which is lost by the metal will be gained by the non-metal and will be getting converted into the anion. And there will be then the force of attraction between the cation and the anion, and that force of attraction is something which we call as ionic bond, right? Now talking about the conditions. What are the conditions for the ionic bond formation? See guys, have a look exactly what are the conditions which must get satisfied for the formation of ionic bond, right? See guys, the first condition for the formation of ionic bond, one element should be metallic and other elements should be non-metallic, right? Then only complete transfer of electron is possible from metal to non-metal, yeah? Then only complete transfer of electron is possible from metal to non-metal. Point number one. Point number two, right? See guys, I told you in the ionic compound, there are two elements, right? One is metal, another one is non-metal, right? Metals, they lose electrons and that electron which is lost by the metal is gained by the non-metal, right? Now, which metal is the good candidate for the formation of ionic bond. That metal is the good candidate for the formation of the ionic bond, which can lose electrons easily. The point is, which element, which metal loses electron easily? That metal loses electron easily, which will be having low ionization energy, right? The metallic element should have low ionization energy. Yes, the metallic element should have low ionization energy. Then only electron will be lost by the metallic element easily. Then only cation will be getting formed easily, right? Similarly, the non-metallic element, which gains the electron given by the metal, it must have high electron affinity so that it can attract the electron given by the metal towards itself fastly in order to get converted into the anion. Once the cation and anion gets generated, then force of attraction comes in between the two, right? That force of attraction is the ionic bond, right? So the conditions for the formation of ionic bond. Metals should have low ionization energy and the non-metals should have high electron affinity, due to which it forms the anion easily, right? So in short, cation should be formed easily and fastly at the same time. Anion should be formed easily and fastly at the same time, right? When is that possible? That is only possible when the metal will have low ionization energy and non-metal will have high electron affinity. Yes, I'm sure it's clear to everyone. Right, people? Harsh, I'm doing great. How are you? No, it's not my birthday. Who told it's my birthday? My birthday is on 6th April. All right, guys, let's move on then. Let's talk about the characteristics of ionic compounds, right? Let's talk about the characteristics of ionic compounds. Some basic characteristics of ionic compounds which you all must remember. Yes. First one, ionic compounds, these are generally hard in nature, right? These are hard. Ionic compounds, they're generally hard. They have high melting and boiling points, right? Due to the strong electrostatic force of attraction between the cations and the anions, right? These ionic solids, they have got high melting and boiling points. Yeah. They act as insulators in solid state, but in molten and aqueous state, they act as good conductors of electricity, right? When the ionic compound will be in solid form, right? Let's say I'm talking about NaCl solid. Right? This ionic compound right now is in solid form. Yes. When the ionic compound will be in solid form, these ions are firmly held by the strong electrostatic force of attraction, right? So there'll be no movement of ions at all. There won't be any sort of movement of ions at all when the ionic compound is in solid form. But when the same ionic compound will be in aqueous form, aqueous means when I'll be putting this NaCl into water, right? Or when I'll take this ionic compound into the molten form. What does that mean? That means when I'll be converting the solid into the liquid, right? Liquid NaCl is something which I call as molten NaCl, correct? When the same ionic compound will be either in aqueous form or in molten form, the ions, they are a little far from each other. Because when we convert solid into the liquid, what happens to the distance between the particles? Distance increases, right? So when I'm converting the ionic compound which is in solid form into the liquid form, what happens to the distance between the ions? It increases. If the distance between the ions increases, force of attraction between them decreases. If the force of attraction decreases, I can say comparatively ions now can show the moment. And when the ions can show the moment, definitely they are going to be good conductors of electricity at that time. So remember, when the ionic compound will be present in the solid form, at that time it's going to be acting as the insulator. But when the same ionic compound will be in molten form or aqueous form, it is going to act like the conductor, right? I'm sure it's clear to everyone. Yes? Let's move on talking about one more thing. They have generally high density, right? Yes, it's simple to understand. Ionic compounds, definitely they'll be having high density. Why is that? What is density all about? Density is equal to mass by volume, right? Density is equal to mass by volume. Due to the strong force of attraction between the cation and the anion, right? These ions are close to each other. If these ions are close to each other, volume occupied by the ionic compound is less. If the volume occupied by the ionic compound is less, I'll say density is more, right? Because density and volume, these are inversely proportional to each other, yeah? I'm sure it's clear to everyone. And at the same time, these ionic compounds, right? If I talk about ionic compounds, or if I talk about ionic bond in particular, they are non-directional. That is why they do not have any geometry, right? This ionic bond, this electrostatic force of attraction, it is non-directional. What does that mean? See, if I'll keep, for example, Na positive over here, right? I've kept Na positive over here. For example, Now, over here I've kept one Cl negative, right here I've kept one Cl negative, right here I've kept one Cl negative, right here I've kept one Cl negative. Is this Na positive going to attract only one Cl negative towards itself? No way, right? See, this is positive, this is negative. It's going to attract this one, even this one, even this one, right? Irrespective of where these Cl negatives are, this Na positive is going to attract every Cl negative towards itself. So, is this force of attraction in a particular direction? Is it unidirectional, right? Is it unidirectional? Yes, it is non-directional, right? It is going to attract all the Cl negatives, all the oppositely charged ions towards itself, which makes it non-directional, right? That's why the ionic compounds, they do not have the particular geometry. They do not have the particular geometry. Whereas, if you take the case of water, right? This is the force of attraction between oxygen and hydrogen. This is the force of attraction between oxygen and hydrogen. Towards particular direction, the force of attraction exists, right? Okay, anyways, I'm going to talk about this in detail afterwards when I'll be teaching the covalent compounds, right? Yes, so remember, these are non-directional. That's why they do not have any geometry in particular, right? Now, people, let's talk about something called as lattice energy. What is lattice energy all about? How do we define the lattice energy? The amount of energy which is released when 1 mole of an ionic compound is formed from its gaseous constituent ions. What does it mean? See, for example, over here, I'm taking 1 mole of gaseous Na positive, right? Over here, I've taken 1 mole of gaseous Na positive. And right here, I've taken 1 mole of gaseous Cl negative. 1 mole of gaseous Cl negative, right? So if I'll be taking 1 mole of gaseous Na positive, 1 mole of gaseous Cl negative, I think I'll be getting 1 mole of NaCl over here, right? Or let me show it to you exactly. The reaction I would have mentioned over here. See guys, I took 1 gaseous Na positive, 1 mole of gaseous Na positives, 1 mole of gaseous Cl negatives, right? Okay, and what is happening? 1 mole of NaCl solid is being formed. 1 mole of NaCl solid is being formed. First of all, you all must be familiar with the fact, whenever there are attractions, energy is released. Whenever there are attractions, energy is released, right? See, Na positive, Cl negative, oppositely charged ions, they are going to attract each other. When they'll be attracting each other, energy will be released. And that amount of energy which is released when 1 mole of NaCl solid gets formed from its constituent gaseous ions, that is something which I'll be calling as the lattice energy of this NaCl, right? That's something which I'll be calling as the lattice energy of this NaCl. So how do I define lattice energy of NaCl here? That amount of energy which is released when 1 mole of NaCl is getting formed from its constituent gaseous ions. As simple as that, yeah? Okay. Since energy is being released because attractions are happening over here, attractions are there, attractions exist. Due to attractions, energy is getting released. And we got to know 1 mole of NaCl is getting formed from its constituent gaseous ions, right? Okay. And whenever energy is released, we call that process as endothermic or exothermic, right? So people, remember one thing, just a second. Okay, remember one thing, energy is released in this process. In the formation of 1 mole of NaCl solid, energy is definitely being released, right? Or at the same time, you can define the same lattice energy in one more way as well. You can define the same lattice energy in one more way. What is the first way to define lattice energy? The amount of energy released when 1 mole of ionic lattice gets formed from its constituent gaseous ions, right? That's one way of defining this lattice energy. What is the another way? See guys, once this NaCl gets formed, there will be strong force of attraction between this Na positive and Cl negative, right? Okay. So in order to break this force of attraction, do we have to supply energy? Yes, energy is required in order to break this NaCl now. Once it gets formed, then in order to break it again, you need to supply energy. The amount of energy which is needed, to break 1 mole of ionic lattice, into its constituent gaseous ions, that's something which we call as lattice energy as well, right? So you can define lattice energy in both the ways. Number one, the amount of energy which is released when 1 mole of ionic lattice gets formed from its constituent gaseous ions, right? The second way, the amount of energy which is needed, which is required, right? When 1 mole of gaseous ion gets converted, 1 mole of the ionic lattice gets converted into its constituent gaseous ions, right? I'm sure it's clear to everyone. Right, guys? Perfect. Now, higher the lattice energy, stable will be the compound. This is obvious now. right? Okay, what is the second definition of the lattice energy? The amount of energy which is needed in order to break 1 mole of lattice, into its constituent gaseous ions, right? See, if more is the lattice energy, that means more is the energy needed to break this lattice, right? And more the energy needed to break the lattice, that means more is the force of attraction between these ions, right? And if more is the force of attraction between these ions, definitely it's going to be stable, right? Yes. As simple as that. Yeah. So higher the lattice energy of the compound, stable it's going to be, right? Because more energy is needed to break it, right? And more the energy needed to break the lattice into its gaseous ions, definitely more stable it's going to be. Yeah. Surely it's going to be clear, right? Now comes the point. Lattice energy is directly proportional to the charge present on ions and inversely proportional to the size of the ions, right? Let me write it over here. Lattice energy, it is directly proportional to the charge present on the ions. Yes, and inversely proportional to size of the ions, right? So first of all, if I'll be having the ionic compound AB, let's say this is A positive, this is B negative, right? Let's say I've got one more ionic compound AB, in which this A is in di-positive form, B is in di-negative form, right? We know force of attraction between the two oppositely charges is directly proportional to the charge present on them. That's something which you all must be knowing, right? Coulomb's law. Force of attraction is directly proportional to charge on the ions. More the charge on the ions, more is going to be the attraction between them. More the attraction between them, more is the energy needed to break it. More the energy needed to break it, more is going to be the lattice energy. So remember, more the charge present on the ions, more is going to be the lattice energy, stable is going to be the compound, right? Similarly, lattice energy is inversely proportional to size. Less the size, more is going to be the lattice energy. In short, more the size of the gaseous, more the size of the ions, less is going to be the lattice energy, right? Let's use this concept and try to solve few equations. See exactly what the equation is all about. I'm good with LiCl, I'm good with NaCl, KCl, RbCl, right? These are the compounds which are given to me. Yeah? These are the compounds which are given to me. Have a look. See guys. Over here, this is Li positive, this is Cl negative, Na positive, Cl negative, K positive, Cl negative, Rb positive, Cl negative. I'll say N ion is same everywhere. N ion is same everywhere. So I'm not going to decide on the basis of the anion over here. Let's keep the anion aside. Let's try to decide on the basis of cation, because cation is changing. Li positive, then comes your Na positive, then K positive, then Rb positive, right? Is the charge present on every cation same, right? The charge present on every cation is same. So I'm not going to decide on the basis of charge as well. Now I'm going to decide on the basis of what? On the basis of size, right? Well, if I talk about Li positive, then comes your Na positive, lithium, sodium, potassium, then rubidium, then cesium, etc., right? All these elements, they belong to the same group, right? And as we move from top to bottom, what happens to the size of these ions? Size of these ions increases. And we know lattice energy is inversely proportional to size. More the size, less the lattice energy. Okay, so which cation has got the maximum size? This Rb positive has got maximum size. Wherever size is maximum, lattice energy is minimum, right? So this is going to be the order of the lattice energies. I'm sure it's clear to everyone, yeah? Yes? Similarly, guys, if you talk about MgO, NaCl, LiCl, have a look exactly how I'm going to approach this sort of equation. I need to arrange them on the basis of lattice energy, yeah? See, this is Mg di positive right here, this is O di negative, this is Na positive, this is Cl negative, this is Li positive, this is Cl negative, right? We know first of all lattice energy is directly proportional to charge. More the charge on the ions, more the lattice energy, right? In the first case, charge present on the ions is maximum. So lattice energy of first one is maximum among all. Lattice energy of first one is maximum among all, because charge present on ion is maximum, right? As compared to the other species. Now, among these two, the N ion is same. I'm not going to decide on the basis of N ion, right? Let's decide on the basis of cation. These two cations carry same magnitude of charge. I'm not going to decide on the basis of charge as well, because charge is same. Let's decide again on the basis of size. Na positive has got more size than Li positive. Wherever size is more, lattice energy is less, right? So second one is going to have least lattice energy. Third comes in between, right? So this is going to be the order of the lattice energies. I'm sure this is clear to everyone. You can give me some confirmation in the chats if it is clear to everyone, so that I can move on to the next one. And do share the video, do like the video with your friends. Do share the video with your friends, do like the video, and do not forget to subscribe to the channel as well. Let me know in the chats if it is clear to everyone. Yes? Right, guys? Let me know in the chats if it is clear to every single guy. Yeah? I'm sure it's clear to everyone. Perfect. Let's move on. Let's talk about the solubility of these ionic compounds, right? Let's talk about the solubility of these ionic compounds. Yeah? There are a few points which you need to take a note of. Let me first of all tell you, ionic compounds, these are more soluble in solvents having high dielectric constants, right? How do we define the dielectric constant of solvent? That's the point. How do we define the dielectric constant of a solvent? Well, in simpler words, dielectric constant of a solvent is the tendency of the solvent to weaken the force of attraction. What does that mean? Have a look exactly. For example, this is the container which I'm taking. This is the container which I've taken over, right? Let's assume in this container, we have got a solvent, water present in it, right? We have got a solvent, water present in it, okay? Now I'm going to put NaCl into this compound, into this water. I'm going to put NaCl into this water. This is Na positive basically, this is Cl negative. There is force of attraction between them, right? The tendency of the water to weaken the force of attraction, to break the force of attraction between these ions in this compound defines the dielectric constant of water. More the tendency of the solvent to weaken the force of attraction, more is going to be the dielectric constant of solvent, right? And that solvent which will be having more dielectric constant, in that solvent your ionic compound can get dissolved. It will be soluble in that solvent, right? See guys, look at the first statement. Ionic compounds are more soluble in those solvents which have got high dielectric constant, right? I think it's simple. I think it's understood, right? More the dielectric constant of the solvent, more is the tendency of the solvent to weaken the force of attraction, right? More is going to be the solubility of the ionic compound, right? Okay. So first point, ionic compounds are more soluble in solvents having high dielectric constant, yeah? Second, water, do remember it has got the maximum dielectric constant and its dielectric constant value is 81, right? Water has got the maximum dielectric constant, right? So water has got the maximum tendency to weaken the force of attraction between these ions, right? That's why we say water is a universal solvent, right? That's why we say water is a universal solvent, right? Most of the substances, they get dissolved in it because water has got the highest dielectric constant. It has got the strong tendency to weaken the force of attraction between the ions, yeah? Okay. And do remember, ionic compounds, these are soluble in water. Why is that? Because water has got the highest dielectric constant. It has got the tendency to weaken the force of attraction between the ions, right? That's how your ionic compound will be soluble in this water. I'm sure it's clear to everyone. Yes, Neha, coordinate bond will be discussed too. Absolutely. Yeah? Okay, now comes one more point that's called as hydration energy. People, have you heard about something called as hydration energy? You can let me know in the chats. What is meant by the term hydration? See guys, first of all, let me make you understand what this hydration is all about. Then we'll be talking about this hydration energy in detail, yeah? Right? See guys, exactly what this hydration is all about. First of all, again, I'm taking water over here in the container. There is water in the container, right? There are millions of water molecules in the container. Now, in this container, I'm, for example, putting Na positive. An ion I'm putting into this water. And an ion I'm dropping into this water. As you all must be knowing, the structure of water is something like this, right? Between oxygen and hydrogen, oxygen is more electronegative, due to which oxygen gets delta negative, hydrogen gets delta positive. Due to this bond, oxygen gets delta negative, hydrogen gets delta positive, right? So what is the net charge present on oxygen? Net charge present on oxygen is -2. The charge present on hydrogen is +1. The charge present on this hydrogen is +1, right? So I'll be calling this oxygen as the negative end of water. I'll be calling these hydrogens as positive ends of water. Oxygen I can call as the negative end of water, and hydrogens I can call as the positive ends of water. Now what I've done exactly, I've kept Na positive in this water, in the water which is in the container. What is going to happen? I'll say negative end of water, which carries the negative charge, right? This end of water is going to attract this Na positive towards itself. Negative end of water is going to attract, yes, is going to attract this positively charged species towards itself, right? So what is happening exactly? I'll say attraction is happening. Attraction is taking place between this Na positive and the negative ends of water, right? Positive negatives, they are going to attract, absolutely. Yes. This phenomenon of surrounding of water molecules towards a particular species, due to the force of attraction between them. This process, this phenomenon is called as hydration. And we know, wherever there are attractions, energy is released. Remember the amount of energy released when 1 mole of gaseous ion undergoes hydration, that amount of energy released is what we call as hydration energy, right? So what is hydration energy all about? Hydration energy is nothing. It is simply the amount of energy released when 1 mole of gaseous ions undergo hydration, right? Okay. So first of all, energy is released in this process, right? Hydration, it's going to be exothermic. It's going to be exothermic because energy is released in this process. Yes, this hydration phenomenon, it's going to be exothermic because energy is released. Yeah? Perfect, guys. Since energy is released, that's why enthalpy of hydration is taken as negative, right? See, that's something which I'll be discussing in thermodynamics. Whenever in any process energy gets released, we call that process exothermic process, right? We call that process exothermic process. Yes. If it is the exothermic process, delta H enthalpy change for hydration is taken as negative. Remember, for any exothermic process, delta H value is taken to be negative. And for any endothermic process, delta H value is taken to be positive. Correct? Right? Which is what we call as enthalpy change. Right, guys? Now comes one more point. Greater the hydration energy, more will be the solubility of the ionic compound. Right? Greater the hydration energy, more will be the solubility of ionic compound. Right? See, guys, solubility of ionic compound in a particular solvent, it depends on two factors. Solubility of an ionic compound in a particular solvent. Solubility of an ionic compound in a particular solvent, it depends upon two factors, lattice energy and hydration energy. Right? So first of all, when an ionic compound is put into water, what happens first? The force of attraction between the cation and anion is to be broken down, right? And in order to break the force of attraction, you need energy, right? Yes. And more the lattice energy of the ionic compound, more is the energy needed to break the ionic compound into its respective ions. And once the ionic compound is broken down into its respective ions, those ions are attracted by the water molecules. Right? Hydration takes place. And whenever there is hydration, energy is released, right? So first, energy is needed to break the ionic compound into its ions, right? Second, those ions are being attracted by the water molecules towards itself, due to which energy is released. So in the first phase, energy is needed. In the second phase, energy is released. Right? Greater the hydration energy, more the energy released. If more is the energy released, that amount of energy which is released in the hydration, that amount of energy is used to break more ionic compounds into their ions. Right? That's how solubility becomes more. Right? Right, people? Let me know in the charts. So remember, greater the hydration of the ionic compound, more is the energy released, and that amount of energy which is released is used to break ionic compounds into their ions. That's how solubility of the ionic compound is more, right? Yes. So remember, solubility of ionic compound is directly proportional to hydration energy. More the hydration energy, more is going to be the solubility of ionic compound into a particular solvent. I'm sure it's clear to everyone, right, people? Clear to everyone? Should I move on? Should I move on? Yes? Alright, now comes the point. Hydration energy is directly proportional to charge on ions and inversely proportional to size of the ions. Do remember this as well. If I talk about hydration energy, this hydration energy, it is directly proportional to the charge present on the ions and inversely proportional to the size of the ions. More the charge present on the ion, more water molecules will be attaching, more water molecules will be surrounding a particular ion. More the charge on the ion, more water molecules will be surrounding it. More the water molecules surrounding it, more will be the energy released. More the energy released, more the hydration. So more the charge on the ion, more is going to be the hydration energy, right? Similarly, less the size of the ion, more is going to be the hydration energy. What does that mean? Less the size of the ion, more is going to be the charge density of the ion, right? Lesser the size of the ion, more is going to be the charge density on the ion, right? And more the charge density on the ion, more water molecules will be attaching it. More water molecules will be getting attached to it, right? And if more water molecules will be getting attached to it, more energy is released. More energy released means more will be the hydration energy. Yes? Yes? So remember from now onwards, hydration energy is directly proportional to charge on the ions, inversely proportional to size. More the charge, right? More the charge, more water molecules will be surrounding it, more the energy released. Lesser the size, more will be the charge density. And if more is the charge density, more water molecules will be attaching it. And if more water molecules are attaching it, more is the energy released. And if more is the energy released, more is going to be the hydration energy. I'm sure it's clear to everyone, right? Perfecto. Now people, let's try to solve these questions. These are very simple questions over here. First question, I need to arrange them on the basis of hydration energy order. I need to arrange these species on the basis of hydration energy order, right? Li positive, Na positive, K positive, Na, Rb positive. I told you a few minutes back, hydration energy is directly proportional to charge on the ions, inversely proportional to size. The charge on every ion is same. The charge on every ion is same. So I'm not going to decide on the basis of charge. I'm going to decide on the basis of size, right? See, lithium, sodium, potassium, rubidium, they belong to the same group, right? And on moving from top to bottom, what happens to the ionic size? Ionic size increases, right? That ion which will be having more size will be having less hydration energy. Rb positive, right? It comes at the bottom of the periodic table, right? So it has got maximum ionic size among all. So it will be having minimum hydration energy. So this is going to be the order. This is going to be the order, right? Yes, this is going to be the order. If I talk about the size, if I talk about the order of the size, see, if you talk about Li positive, then we have got Na positive, we have got K positive, we have got Rb positive, etc., Cs positive, right? On moving from top to bottom, they belong to the same group. On moving from top to bottom, what happens to ionic size? It increases, it's normal, right? It increases. Yes, on moving from top to bottom, ionic size increases. So this is the order of ionic size, yeah? Okay. All right, let's have a look on the hydrated size. Let's have a look on the hydrated size. See, this is Li positive, Na positive, K positive, Rb positive, right? Charge on every species is same, but size of Li positive is minimum among all. If size of Li positive is minimum among all, so Li positive will get hydrated the maximum among all these species. Li positive will get hydrated the maximum. There will be maximum water molecules attached with this Li positive. There will be maximum water molecules that are attached with this Li positive, right? And if there are maximum water molecules attached with this Li positive, so the size of this hydrated ion will become maximum among all. Size of this hydrated species, hydrated Li positive will be maximum among all, because maximum water molecules are attached with it, right? The size of hydrated Na positive will be comparatively smaller than that of hydrated Li positive. The size of hydrated K positive will be less than that of the size of Na positive, right? That ion which gets hydrated the maximum, right? Its hydrated size will be maximum, right? So which ion is going to have more size in hydrated form? So it's going to be Li positive aqueous followed by this, right? Okay. Similarly, if you talk about the mobility, of these hydrated ions, which ion got hydrated the maximum? Li positive got hydrated the maximum, right? So which hydrated ion has got the maximum size? Li positive has got the Li positive in aqueous form. Li positive hydrated, it has got the maximum size. If it has got the maximum size, is it going to move slowly or fastly? More the size, less the mobility, right? Yes, it has got the maximum size among all. It's going to move slowly, right? Its mobility will be less. So what is the mobility order? Mobility order will be like this. Mobility means moment, right? Mobility means simply moment. Yes? Right? Now people, remember, more the moment of the ions, more is the conductivity. More the moment of the ions, more is the conductivity. Which hydrated ion is showing the low mobility? This hydrated ion is showing low mobility. So its conductivity will be minimum, right? More the mobility, more the conductivity. Less the mobility, less the conductivity, right? Less the mobility, less the conductivity. So this is the order of the conductivity as well. I'm sure it's clear to everyone. You can let me know in the chats if it is clear, so that I can move on and talk about a few more interesting things, right? And the ones who have not liked the video yet, do like the video, share the video to friends, and do not forget to subscribe to the channel as well. Okay? Let me know fast in the chats, guys, if it is clear to every single guy. Okay. Okay, so let's move on and let's talk about something called as covalent compound as per the Lewis concept is concerned, right? What is covalent compound all about? What is covalent compound? Covalent compound is the one which contains covalent bond. What is a covalent bond? Covalent bond is something which gets formed by the mutual sharing of electrons, right? You must have heard about it. Yeah? Every atom, why it forms a bond? As per the Lewis concept is concerned, every atom, it just wants to complete its outermost shell with 8 electrons or 2 electrons. It just wants to complete its octet or duplet, right? That's why it tries to share the electrons, right? In order to complete their respective octets or duplets, right? Okay. Now, let me show you exactly how the structures are to be drawn as per the Lewis concept is concerned, right? See, first of all, there are a few points which you must take a note of. What are those points? Have a look, then I'll be moving on to the structures, right? I'm going towards these points firstly because these are simple and basic and you must have heard about these before also. The bonds formed between two atoms by mutual sharing of electrons between them so as to complete their octets or duplets, that's what we call as covalent bond. The number of electrons contributed by each atom is known as covalency, right? The number of electrons contributed by each atom is called as covalency. Let me give the example. See guys, if I talk about one atom of chlorine, right? Chlorine belongs to group 17 element, right? Chlorine is a group 17 element. Group 17 elements have got 7 electrons in their outermost shell. So this chlorine, it has got these 7 electrons in its outermost shell, 2, 4, 6 and 7. Similarly, this chlorine, 7 electrons in its outermost shell, right? So every atom, it wants to complete its octet or duplet. So this chlorine would want to get 1 electron so as to complete its octet. This chlorine would want to get 1 electron so as to complete its octet. So what they are going to do? They are going to share one electron. And how they are going to share? Have a look. This is the shared form of this, right? Okay. Have a look exactly. This chlorine, its octet is complete. It has got 8 electrons now. Even this chlorine, its octet is complete, right? And this electron pair which is in the middle, it is being mutually shared by 2 chlorine atoms. It is being mutually shared by 2 chlorine atoms, right? This electron pair I'll be calling as the shared pair of electron. That electron pair which is mutually shared by the atoms, right? In the covalent bond formation, that's what I call a shared pair of electron, or you call it as the bonded pair of electron as well. You call it as the bonded pair of electron as well, correct? Now people, remember, those electrons of the atom which belong to the valence shell, but do not participate in the bonding, those are called as non-bonding electrons, or you call them as the lone pairs. See, these 2 electrons, they belong to the valence shell of chlorine, but they have not participated in bonding. These two electrons, these two, right? These are the electron pairs which actually belong to the valence shell of chlorine, but they do not participate in the bonding. And that electron pair which belongs to the valence shell, but do not participate in the bonding, that's what we call as lone pair. So this is a lone pair, 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 right? Yes, you call them as the lone pair of electrons, or you call them as the non-bonding electrons, yeah? Right? Similarly, if you look at HCl, right? Hydrogen has got just 1 electron. Chlorine has got 7 electrons in its outermost shell. So chlorine wants 1 electron, even hydrogen wants 1 electron. Chlorine wants to complete its octet, hydrogen wants to complete its duplet. So they are going to share this electron pair, right? Now if you look, hydrogen completed its duplet, chlorine completed its octet, right? Is there any valence electron of chlorine which has not participated in the bonding, right? There are 3 electron pairs of chlorine which belongs to the valence shell of chlorine but have not participated in the bonding. So I'll be calling these 3 electron pairs as the lone pair of electrons, right? Is there any electron pair on hydrogen as such which belong to its valence shell but has not participated in the bonding? No. That means hydrogen does not have any lone pair of electron, right? Yes? Now we will moving ahead. Remember, during the covalent bond formation, when each atom contributes 1 electron, the bond formed is called a single bond, right? As you saw. In case of 2 chlorine atoms, right? Chlorine, it has some 7 electrons. 2, 4, 6 and 1. 7 electrons, its valence shell. This chlorine, even it has got some 7 electrons in the valence shell, right? Okay. Now, when each atom contributes 1 electron, this chlorine is contributing 1 electron, this is contributing 1 electron. So I'm going to keep these 2 electrons in the middle, right? then I'm going to represent it like this. Okay? When each atom contributes one electron, the bond which gets formed in between is what we call as single covalent bond, right? And at the same time, when each atom contributes 2 electrons, for example, if I take the case of O2, this is one oxygen atom, this is one more oxygen atom. How many valence electrons are there with oxygen? There are 6 valence electrons with oxygen. Similarly, 6 valence electrons with this oxygen as well. Oxygen group 16 element, right? This oxygen needs 2 electrons to complete its octet. This oxygen needs 2 electrons to complete its octet, right? So what is going to happen? This oxygen is going to contribute 2 electrons and the other one is also going to contribute 2 electrons, right? So that these two electron pairs are shared by both these atoms, right? Okay, and when each atom contributes 2 electrons, the bond formed is what we call as double bond. So you can represent it like this as well. This O double bond O, 2 lone pairs on this oxygen, similarly 2 lone pairs on this oxygen, right? This was Cl, single bond Cl. 3 lone pairs on this oxygen, this chlorine, and similarly 3 lone pairs on this chlorine as well, right? So in short, when each atom contributes 1 electron for the bond formation, the bond is going to be single covalent bond. When each atom contributes 2 electrons, the bond is going to be the double covalent bond, right? And when each atom contributes 3 electrons, the bond is going to be triple covalent bond, as in the case of N3, right? Sorry, as in the case of N2. This is how your N2 looks like, right? Okay, there'll be 1 electron pair in the form of lone pair on this nitrogen, in the form of lone pair on this nitrogen, right? Okay, I'm sure all this is clear, yeah? So this is the covalent bond formation of oxygen, this is the covalent bond formation of nitrogen, right? As you saw exactly, okay? This is something which I told you, the shared pair of electron present between the atoms are called as bonded pair of electrons because they are responsible for the bonding between the atoms, right? On the other hand, the valence electrons which are not involved in the bonding, right, are called as non-bonding electrons, or you call them as the lone pair of electrons, right? That's something which is understood. Now the point is how we are going to draw the structures of different compounds by means of this Lewis theory, right? Okay, see guys, what you guys will be doing. See what you all are going to do. Let me try to make the structure of this CO, carbon monoxide, by means of Lewis dot structures. How am I going to draw the structure? First of all, have a look. If I ask you about the carbon, how many valence electrons this carbon has? Carbon has got 4 valence electrons. It has got 4 electrons in its outermost shell. What about this oxygen? It has got 6 electrons in its outermost shell, right? How many total electrons are there with carbon monoxide? Total valence electrons I'm talking about, 6 plus 4, 10. So there are total 10 valence electrons present with this carbon monoxide, right? Yes. 10 valence electrons means how many valence electron pairs? I'll say 5 valence electron pairs are there with carbon monoxide. 1 electron pair is made up of 2 electrons, right? So 10 valence electrons means 5 electron pairs. Yeah? Right? Yes. Now guys, what you are going to do, see, this is carbon, this is oxygen, correct? Put a single bond between these two. Put a single bond between these two. Single bond means 2 electrons. 2 electrons means 1 electron pair. So total I had 5 valence electron pairs. Out of 5, I have used 1 electron pair. I've used 1 electron pair, right? I've used 1 electron pair. Now, after drawing this bond, after using 1 electron pair, right, which is going to be over here, you are going to represent it either like this or you are going to represent it like this, right? You have used 1 electron pair. Now there are 4 left. There are 4 left, right? How am I going to arrange them? Now which one is more electronegative among the two? Oxygen is more electronegative among the two, right? So let's try to complete the octet of this more electronegative element. See, this oxygen right now it has got only 2 electrons. 2 to 4, 4 to 6, 6 to 8. I'll say octet of oxygen is complete. See, 2, 4, 6, 8, right? I had total 5 valence electron pairs. Out of 5 valence electron pairs, how many I have used? 1, 2, 3 and 4. There is 1 electron pair left as such, which I'm keeping on carbon, right? Now if I ask you, is the octet of carbon complete or not? You'll say no. Why? Because it has got 1, 2, 3 and 4. This carbon has got only 4 electrons in its outermost shell right now, but it should have 8. So what you need to do, remove one of the lone pair from here and put up 1 more bond. Remove one more electron pair from oxygen, put 1 more bond. Now check the octet of each atom over here. Check guys, oxygen 1, 2, 3, 4, 5, 6, 7, 8. Octet of oxygen is completed. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Octet of this carbon is also completed, right? Yes? So this is the structure of your carbon monoxide as per your Lewis theory is concerned, right? I'm sure it's clear to everyone. Right, people? Perfect. Let's move on. Let me take a few more examples so that you get trained in it properly. If I talk about NO2 negative, this is NO2 negative. Calculate the valence electrons of every atom over here. Yes? Have a look. How am I going to do it? Nitrogen belongs to group 15 elements. And group 15 elements, they have got 5 electrons in their valence shell. So 5 electrons with nitrogen. Oxygen, group 16. 6 electrons in its valence shell, but we have got 2 oxygen atoms multiplied by 2. And there is a negative charge over here as well. If there is negative, add this negative. If it was -2, I used to add +2. If it was -3, then +3. -4, +4, right? If it was +1, then over here -1. +2, -2. +3, -3, and so on, right? If there is a negative charge, add it. That's all. So it comes out to be 5 + 6 to 12, right? +1. 5 + 12 means 17 + 1, 18. So there are total 18 valence electrons with all these atoms. 18 valence electrons. 18 valence electrons means 9 electron pairs. 9 valence electron pairs, right? 9 valence electron pairs, right? Now, is it a diatomic species or triatomic species? It's a triatomic species, right? As you can see, 3 atoms in it. Triatomic species. Now, which atom is going to be the central one? Which atom is going to be the central one? That atom, you'll be taking the central one, which will be less electronegative. Among nitrogen and oxygen, which one is less electronegative? Nitrogen is less electronegative. So nitrogen you are going to keep as the central atom, right? Then one oxygen, for example here, right? After this, put a single bond everywhere. Put a single bond everywhere, right? Put a single bond everywhere. So how many electron pairs we have used till now? 1 and 2. 2 electron pairs I've used. How many I had? 9. Out of 9, how many I've used? 2. How many are left? 7. Now fill the octet of the more electronegative element. More electronegative element is oxygen. Let's say I'm filling the octet of this oxygen. 2, 4, 6, and 8, right? Octet of this oxygen is completed, right? Okay. How many electron pairs I had? 9. Out of 9, how many I've used? 1 electron pair, 2, 3, 4, 5. There are 4 electron pairs as such, right? Fill the octet of this more electronegative element. So octet of this electronegative element is also filled, correct? Right? So how many I've used till now? 3, 4, 5. 5 + 3, 8. There is 1 electron pair left as such that I'm going to give to the nitrogen. See, octet of this is complete, octet of this is complete, but octet of nitrogen is not complete. Right? Why is that? Because nitrogen right now has got 1, 2, 3, 4, 5, 6. 6 electrons in its outermost shell, but it needs 8. So what you need to do, out of these oxygen atoms, you can remove any one of the electron pair from any of the oxygen atoms and put a double bond. That's all. From here you can remove, or from here you can remove, put a double bond over here. Choice is all yours, right? This is the structure of your NO2 negative. You can check, is the octet of every species completed, right? Octet of every species is completed. You got to know there are 1, 2, 3 bonded pair of electrons. There are 2 lone pairs on this oxygen. There are 3 lone pairs on this oxygen. There is 1 lone pair on this nitrogen. Every single thing is clear, right? Let me know in the chat if it's clear to everyone. Yeah? Let's move on. Let me take a few more cases. If I talk about HCN, hydrogen has got 1 electron in its outermost shell. Carbon has got 4. Nitrogen has got 5. 5, 4, 9, 1, 10. So 10 electrons, 10 valence electrons as such, right? 10 valence electrons means 5 valence electron pairs. So arrange these 5 valence electron pairs, right? Arrange these 5 valence electron pairs. So let me keep carbon over here. Let me keep nitrogen over here. Let me keep hydrogen over here. Let me put a single bond in between everyone. Put a single bond, right? So how many electron pairs I had? I had some 5 electron pairs. Out of 5, I've used 1, 2. So 3 are left. Now fill the octet of more electronegative element. 1, 2, 3, 4, 5, 6, 7, 8. Octet is completed, right? Okay. Now guys, have a look. How many electron pairs I had? 5. Out of 5, how many I've used? 1, 2, 3, 4, 5. All the 5 I've used, right? But no doubt octet of nitrogen is complete. But is the octet of carbon complete? Octet of carbon is not complete. 2 and 4. Only 4 electrons in its outermost shell, but it needs 8. So remove one of the electron pair from here, put a double bond, right? Remove one more electron pair from here, put a double bond, right? So check the octet of every atom. Octet of this is complete, 1, 2, 3, 4, 5, 6, 7, 8. Octet of carbon is complete, 8, and duplet of hydrogen is also complete, 1, 2, right? This is the structure of your HCN. Right, guys? Right? Perfect. All right, let's move on. Let's see a few more structures. If I talk about CO3 dinegative, CO3 dinegative, right? Let's make its structure. So first of all, carbon, it has got 4 valence electrons. Oxygen has got 6, 6 3s are 18. Dinegative, add these two, right? So 18 plus 2 means 20 plus 4, 24. So 24 valence electrons in total, which means 12 valence electron pairs, right? Now arrange these 12 valence electron pairs. So first of all, select the central atom. The one which is less electronegative, carbon, right? Carbon is the less electronegative element, okay? I'm selecting carbon over here, right? It is a central atom. One oxygen over here, one oxygen over here, one oxygen over here, for example, right? Put one single bond, one single bond, one single bond. So out of 12 electron pairs, I have used 3. Now I'm going to fill the octet of the more electronegative element like oxygen. Fill the octet of this oxygen first, right? Octet of this oxygen is complete. 2, 4, 6, 8, right? 2, 4, 6, 8. So how many electron pairs I had in total? 12. Out of 12, how many I have used? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Now if I ask you, no doubt, octet of this one is complete, octet of this one is complete, octet of this one is complete, but is the octet of carbon complete? Octet of carbon is not completed. A carbon right now, it has got only 6 electrons in its outermost shell. So just take any one of the electron pair out from any of the oxygen. For example, I'm removing the electron from here and instead of it, I'm putting a double bond. Now the octet of carbon is also complete, 2, 4, 6, 8. This is the structure of your CO3 dinegative, right? I'm sure it's clear to everyone. Right, guys? Yeah? Right? See, I just wrote the charge over here, right? Now you have no idea on which atom exactly the charge is. On which atom exactly the charge is. You have no idea about that, right? How come I'll be getting to know that? How come I'll get to know that on which atom exactly the charge is? Formal charge is going to give me the idea about that. On which atom exactly this charge is, right? Yes? Okay. Let's make the structure of carbon dioxide. CO2, right? All of you must be doing. Carbon has got some 4 valence electron, oxygen 6, 6 multiplied by 2, 12, right? So 12 plus 4 comes out to be 16. So 16 valence electron pairs means, 16 valence electrons in total means 8 valence electron pairs, right? Now, among carbon and oxygen, carbon is less electronegative. It's going to be the central atom. This is one oxygen, this is one more oxygen. Put a single bond. Out of 8 electron pairs, I've used 2 electron pairs. Now fill the octet of more electronegatives. 2, 4, 6, 8, right? 2, 4, 6, and 8. Okay, so 8 electron pairs I had in total. Out of 8, I've used 1, 2, 3, 4, 5, 6, 7, 8. I've used all the 8 electron pairs. Now, the point is the octet of carbon complete? No way. So just remove one of the electron pair from here, right? Remove one of the electron pair from here, put a double bond. Remove one of the electron pair from here, put a double bond. This is the structure of carbon dioxide. That's all. Yes? I'm sure it's clear to everyone. This is clear now. Yeah? So let me see if I have more examples or not. Just a second. Okay. This is your homework. Do let me know how many total lone pairs are there on O3. Do let me know in the comment box afterwards how many total lone pairs are there in O3, right? How many total lone pairs I'm asking? Total lone pairs, right? So do let me know about that. Dakshin, odd electron species I'll be showing you in the next session, bro. Not here, right? Okay, NO3 negative we can make 2, right? Okay. Let's make the NO3 negative first, then I'll be making Cn negative as well. Just a second. NO3 negative. Let's calculate the valence electrons first of all. Nitrogen has got 5, oxygen has got 6, 6 3s are 18, plus 1 due to this negative charge. So 18 plus 1, 19, 19 plus 5 is 24. So 24 valence electrons in total means 12 electron pairs, right? 12 electron pairs. Among nitrogen and oxygen, nitrogen being less electronegative, so nitrogen over here, one oxygen, one oxygen, one oxygen, correct? Yes. Put a bond. I've used 3 electron pairs. Now fill the octet of more electronegative elements. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, right? I had 12 electron pairs. Out of 12, I have used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used all the 12 electron pairs, right? But is the octet of nitrogen complete? No way. Nitrogen has got only 6 electrons in its outermost shell. So remove one of the electron pair from any of the oxygen, put a double bond. This is going to be the structure of your NO3 negative, right? But on which atom this negative charge exactly is? That's something which formal charge is going to let me know about that, right? Formal charge concept is going to let me know on which atom exactly the charge is. That's something which we'll be discussing too. Yeah? Right? Okay. Cn negative. Cn negative. This you can draw on your own, I assume. Correct? Right? Okay, so Cn negative is drawn over here already. Yeah? Cn negative is drawn over here already. The structure is going to be same as that of HCN. Correct? Right? Okay, facts unknown, no, you cannot make a triple bond in carbon dioxide, bro, because oxygen is divalent. Right? Okay, O2 di-negative. Oxygen, 6 electrons, 6 twos are 12, 12 plus 2 is 14. So 14 valence electrons in total means 7 electron pairs, 7 valence electron pairs, right? So this oxygen, put a single bond, right? Put a single bond. 7 electron pairs in total. Out of 7, I've used 1. I'm using one more electron pair. I'm using one more electron pair. Using one more electron pair. One more on this. One more on this oxygen. One more on this oxygen, right? So I've used all the 7 electron pairs, correct? But is the octet complete? Right. Octet of every oxygen is complete. So this is going to be di-negative over here. This is the structure. As simple as that. Yeah? Yes? Perfect. So people, this is something. Formal charge is something which I'll be discussing in the tomorrow session, right? Let's stop till here because I've got one more session coming up on Vedantu JE English channel at exact 10:30 tonight, in which I'll be discussing chemical equilibrium. If you want to get trained in chemical equilibrium, today is the first session of the chapter chemical equilibrium on Vedantu JE English channel, in which I'll be taking that chapter at 10:30 sharp, right? And this formal charge is something which I'll be discussing in the next session, and the next session we'll be discussing the odd electron species as well, right? Okay, before ending the session, the ones who have no idea about the actual Vedantu platform, right, people, if you want to be the part of actual Vedantu platform, if you want to get trained by us on all the 3 subjects, in all the 3 subjects, you need to take any of these plans, right? Well, no need to take this. No need to pay this much of amount in one go. You can pay this much amount in installments, right? And if you're new to Vedantu, you have no idea how the actual Vedantu platform looks like, you can take the subscriptions for the month. For 1 month through this light plan, you have to pay this much of amount, right? For this classic, you have to pay this much of amount, and for this one, you have to pay this much of amount, right? You can actually give it a try for a month. If you think you are getting benefited, then you can go for the 2-year classroom programs, right? Okay, so it's my personal suggestion for you guys to get enrolled to the actual batch, to the actual Vedantu platform for a month at least. Then you'll get to know what the actual concepts are all about, right? So people, with this, I'm going to take a leave. There's a Telegram link in the description box of the video. You need to click on this link, get added to the Telegram group, stay updated about the classes. The ones who have not liked the video, please do like the video, share the video with your friends, do subscribe to the channel as well, right? So at the end, let me show you exactly how to get enrolled in this, right? See guys, this is the video which you guys are currently watching, right? This is the video which you guys are currently watching. You need to drag it down, click on this show more. After clicking on this show more, you'll be getting a lot of links. If you want to get CBSE Term 1 crash course, click on this link. After clicking on this link, you will be getting 2 plans. Either you'll be getting the crash course through light plan or classic plan, right? Okay. You can click on this buy complete course, right? And use the coupon code WSPRO. You'll be saving some additional 10%, right? Apart from this CBSE crash course in which you can get enrolled in, you have got NEET 2-year classroom or grade 11-12 science or CBSE Term 1 and Term 2 long-term course, right? So let me select this NEET 2-year plan, right? Over here you've got 3 plans as I've shown you. This is light, classic and plus. The choice is all yours, which plan you want to take, right? You can give it a try for a month. For example, I'm giving it a try for a month. I'll be putting my number, my email ID on which I'll be getting the OTP and everything, right? So do get enrolled in this. It's going to be highly beneficial for you, right? See it for a month at least. See it for a month. It is actually going to be beneficial for you. Trust me on that. Okay? And the homework question which I gave you, do let me know its answer in the comment section. So with this, I'm going to take a leave. I'll see you guys sharp at 10:30 on Vedantu J English channel, in which I'm going to start the chemical equilibrium. Till then, you guys take care. Bye-bye. God bless you all and love you all. Take care, guys.